All right, it looks like it's 1 p.m., so let's get started here. Hi, everyone. Welcome to the third day of the MTV Nuclear Engineering Summer School. I'm Farah Rafi from the University of Michigan, and I'll be monitoring today's talk. I am happy to introduce today's speaker, Dr. Manat Shah. Dr. Shah, a verification technologies engineer at Oak Ridge National Laboratory since October 2023, specializes in research and development related to nuclear safeguards and security for conventional and advanced reactors. Before joining Oak Ridge National Laboratory, he held positions at the Canadian Nuclear Safety Commission and Canadian Nuclear Laboratories, focusing on safety analysis for Canada deuterium-uranium reactors, small modular reactors, and the development of a four-dimension, four-pillar and radiation assessment tool for the Canadian Nuclear Safety Commission Emergencies Operations Center. Dr. Shah has a history of impactful contributions, such as designing and facilitating in-field verification exercises for the International Atomic Energy Agency, their international training course on state systems of accounting and for control of nuclear material at Oak Ridge National Laboratory during his time at Tetra Tech. Dr. Shah holds a PhD in nuclear engineering from Texas A&M University, a master's in nuclear engineering from Pandit Deendayal Petroleum University, and a bachelor's in electronics engineering from the University of Mumbai. Dr. Shah, please feel free to take it away.
Thank you very much. And I'm glad to see so many participants joining, so that's great. And I guess I apologize for not being able to join on in person for those who are in the room. And apart from that, to start with the talk, I'll go a little bit building block wise, considering this first week is about basics. So what I'll do is talk about safeguards, what is then safeguard by design, talk about safeguard by design in advanced reactors, and kind of that way we'll put it in the order. And okay, so now if we have to start with what is safeguards, and not to go to the definition level and kind of say, but it is essentially a set of measures to verify nuclear material that it is not diverted or misused in a nuclear facility. And if we have to think about and over the focus over here, it's essentially international safeguards, which is essentially monitored by the IEA, the International Atomic Energy Agency. While there are international safeguards in place, there are also domestic safeguards. And the focus is not there, but it's essentially managed by the state or by the nation so as to facilitate, in some sense, the international safeguards. When we talk about this, that international safeguards is applied by the IEA, and it's kind of verifying the nuclear material declarations and thereby not misuse. Do you think that they are applying it everywhere? And considering the size, I'll answer it myself over here, whether it's kind of applied in every state or not. And the answer is no. It's not applied everywhere. It depends on kind of various aspects, and one of them is the legal framework. Now, essentially, what legal framework here means is what governs that the international safeguards can be imposed, right? And it starts basically from the IEA statute. That's a foundation of the IEA, essentially, what it covers. Then there is NPT, the Non-Proliferation of Nuclear Weapons Treaty. There are other regional treaties as well on nuclear weapons free zones and whatnot. And if you have to go next step in terms of if there are legal bindings, but then what are the instruments, how they can be imposed. And if you have to talk about that, the first one that comes to the front is the Comprehensive Safeguards Agreement. And presently, if I got my numbers right, it's essentially about 188 states have safeguards agreement in place. and about of them, I think they are able to confirm in 130 or 130 about or something of them, if I got the numbers right. But then, apart from the comprehensive safeguards agreement, there are a few more. One of them is voluntary offer safeguards agreement, and which is for any comments if you want to share. I'll go back for a second in the terms of CSA. They are essentially for non-nuclear weapon states that are party to the NPT. And any answers for VOA from the audience? It's essentially for, oh, I see some, there's a different, and they're saying, I can't hear. Are you able to hear me?
Yeah, Dr. Shah, you're coming through great. Don't worry, we'll handle the Q&A.
Cool. So the VOA is essentially for nuclear weapon states which are 5 of them. And then item-specific agreements, which are essentially states that are not party to the NPT and have some specific location sites that are under safeguards, international safeguards with IEA. And then the last one is the additional protocol. So subsequent to CSA, the additional protocol came in play where it essentially provides more means for the IEA to impose safeguard measures to verify their declarations and misuse. Now, if you have to list down the set of nuclear facilities that could be or that are subject to safeguards, and to start from the top, it's the mining and milling. Then comes the conversion and enrichment facilities. Comes the fuel fabrication where the fuel are manufactured. Essentially, up to this point, all of these are called bulk facilities, where the material is in the bulk form. Subsequent to that comes the reactor spent fuel pool, where the fuel are essentially in the fuel assembly form, being used in the reactor for energy purposes, nuclear energy purposes. Then comes to the spent fuel stored for intermediate storage or for long storage until the permanent repository works out, or being sent to reprocessing for where they are reprocessed. So that the last one falls under bulk facility again, where the material is now kind of loose. And the last of it is the waste facility, where everything from all other facilities, the waste, either low level or high level waste, are discarded too. And now talking about the difference in some sense between CSA and additional protocol, from the initial days, the CSA where it was applicable, it was used to cover essentially in between everything from conversion to the reprocessing. But with the addition of enforcement of additional protocol in states that have signed and put in place, they are able to cover also R&D centers as well as any manufacturing units that in some sense provide technology for supports nuclear energy, nuclear technology. Now, while we are talking about that, safeguards will be applied and the IEA verifies it. But then what is verifying the material and whatnot? But then what is the exact role of safeguard measures? And if we have to say it out, it will be in brief words, it's to do assessment of correctness and completeness of a state's declaration. And it's related to nuclear material as well as nuclear related activities. Now, if you think about it, which one do you think is the bigger or the main set, or which is a subset of it? Correctness or the completeness? And if I give it a second to see if any of you guys would like to respond, if not, I'll move forward. And it's essentially correctness is a subset of completeness, where you're verifying the correctness of some particular aspect of declaration, but then completeness is verifying that the declaration itself is complete. And then if you have to think, do you verify correctness? That would be the safeguard measures. And there are various ways. One of them or few of them is nuclear material accountancy, that you account and check the account reported documents. And then you apply containment and surveillance measures. Containment is to control that you can maintain knowledge of it. And then surveillance is to use video cameras and things like that. In terms of verifying completeness, that's where the major effort lies in some sense, behind the scene, where we rely on various sort of information to form a bigger kind of form a bigger picture about the state. May that be information from undeclared, to verify the absence of undeclared nuclear material and activities in a state. The sources would be geospatial images, satellite images. That could be publications from various organizations within the state, things like that. That would be assessed for completeness. And then one of the major aspect when we're looking at the under the nuclear material accountancy aspect would be the inspections, where the inspectors from the IEA would go and visit the facilities. And there are various types of inspections, but essentially they are going and verifying some declaration based on the effort or whatever they are verifying. The inspection type is defined. So if you have to talk about the normal one will be the routine inspection, which is scheduled. It can be scheduled and can be unannounced, or it can be short notice inspection to a nuclear facility. And I think short notice are 48 hours, I believe, 24 to 48 hours window. Then safeguard visits, they are essentially from during construction phase onwards to the decommissioning phase when the safeguard visits happens. And this are essentially in some sense to verify the DIQs. Now to talk about the safeguard process in general, how the IEA kind of goes about applying safeguards, reviewing information and whatnot. And to start from, let's say they have collected whatever the sources of information available and whatever's provided, they'll collect that information and evaluate whether the all informations are available or not. Based on that cycle, they'll identify are there any additional measures required or change in approaches required or not. Based on that, they'll apply measures in the subsequent year, do verification activities, collect other sort of informations. And again, at the end of the year, kind of assess all of this information to draw a conclusion about the safeguards, the success of safeguard measure in some sense, and draw a conclusion. And the drawing this conclusion about correctness and completeness is only for states where states have signed comprehensive safeguards agreement and additional protocols are enforced. For rest of them, it's only limited to correctness of declarations. Now, switching to the topic of safeguard by design, it's essentially safeguards when the design takes into account how safeguards may be applied by the IEA in the future, thinking that proactively and accounting for it in the design stage is the safeguard ability. And while this is voluntary, it's essentially in some sense best practice for various reasons that will be I'll highlight in the next few slides. And this approach of doing safeguard by design is applicable to the whole nuclear fuel cycle, starting from mining and milling to the waste facilities, whatever the facilities may be, that state may have. Now, to kind of give a top level, the concept of what is the safeguard by design concept, it can be either at a facility level, which would be particular, let's say it's a reactor that the facilities under that we are trying to do safeguard by design. And in that case, whatever the fuel cycle, whatever the fuel comes in at the reactor facility, how it's being used, how it flows through the reactor, how long it stays and whatnot. And all of that aspects, when we account for it, the stage design stage, that would be facility level concept of say, SPD. But when we look at the whole state level fuel cycle, how the fuel cycle changes in the state, and think about that and applying the safeguard by design for the whole thing, that's a kind of a state level concept. And in terms of the type, either it could be component or process level where only a certain particular aspect in the facility is changed. May that be valve changes, a change in the valve or change in the pump, something like that. That would be something at a process or component level. When we look at the facility level, it's essentially designing the facility or kind of provision to the IEA, what the change is at the facility level. And then state level safeguard by design would be, in some sense, the state infrastructure needs or the efforts to make provisions in their for accounting for safeguards. Things like that would be at the state level approach and type. Safeguard by design benefits. Now, if you have to kind of look at the very first thing would be that with the incorporation of safeguard by design, the 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 burden on operators, the facility owners reduces. It optimizes the resources. It minimizes IEA efforts as well in terms of inspections. It may involve deploying kind of remote monitoring systems or kind of putting in place other measures that kind of allows them to limit their inspection activities as well. Another is the retrofit, that if the design is in some sense kind of operational to a stage or its design and then comes the IEA, then the change in kind of changing in the facility design to account for it, to put in a new system in place for them to do their verification, to support their verification, that costs a lot. That changes a lot of aspects, including safety requirement for the facility. That involves a lot of cost in terms of making changes to the procedure manuals and whatnot. So it reduces that retrofitting cost as well. Economic reasons as well provides that. Another is the joint use. When you think about it, while the state may deploy their systems for their national safeguards, domestic safeguards, the IEA will be planning to deploy their own measures as well for performing the international safeguard verification and supporting from the start while at the design stage allows them to work on essentially employing a joint use equipment that could serve both of their needs. Obviously, this requires still its own effort, but allows them to minimize the costs associated with each of them. But while it's all hunky-dory, in a way, yeah, safeguard by design is great. We should do it. There are its own challenges, right? There are always two sides of coin. And in this case, when we think about the new facilities, the safeguard needs to be kind of will be applied for, including on any type of nuclear facilities. And it's only, while we are discussing, it's mainly limited to the non-nuclear weapon states. And the main challenge lies is that many of the designers are unaware of this requirement that the owner, the facility owner or the operator will need to obey with or meet the requirement with. Then in terms of new advanced reactors, considering the designs and whatnot, the advanced measures will be required, which raises its own challenges as well. And to talk more about that in terms of not applying for new nuclear facilities, but there are other additional challenges that are associated with advanced reactors. To start with, the fuel itself. If you talk about advanced reactor in the sense, let's say, pebble bed reactors, high temperature gas cooled reactors, then they are using higher enrichment than the conventional light water reactors. Hello fuel. Similarly, molten salt, they have their own higher enrichment level, including breeding blankets as well. And the designs also, they are much different compared to using a fuel assembly and conventional. In the conventional reactors, they are liquid metal cooled, where it's not water anymore, it's liquid metal, which is different how it needs to be handled, and there are safety associated with them. Molten salt raises its own, considering it circulates through the whole react primary system, which is unique in the sense that prior experience in any power reactor doesn't exist. And then high temperature gas cooled reactor as well, how they are comparatively high temperature, what their operating temperature conditions are. And with this new advanced reactor design and the technology comes the aspect of supply management, including the small modular reactors, which are planned to be factory built, and there would be floating type reactors as well, marine. And then new type of fuel management will require compared to the dry cask arrangement for the light water reactors. The storage and the waste form will differ. And another challenge with advanced reactors of particularly micro reactors and small modular reactors would be the full footprint. Being smaller leads to limited access, means limited opportunity for IEA to go on and kind of do the inspections. Now, so now in the last set of slides, like 6, 7 set of slides, I'll talk about 3 types of advanced reactor designs and some of the safeguards challenge associated with them, as well as some of the experience associated with them. And to start with the high temperature gas cooled reactor, most of them are essentially helium cooled reactor designs. There are still other versions of it. And they utilize either TRISO in a pebble form or in a compact form in a fuel rod form. And the fuel here varies from either LE or HELO fuel. And I don't know if there is a need to describe the TRISO, but essentially it's a fuel is sitting in a center of a sphere with there are essentially 3-4 layers of graphite layers or silicon carbide layers that essentially serves as an inherent barrier and provides a high melting temperature as well for these fuels. Um, either in a prismatic shape fuel assemblies or in a pebble bed reactor format. Another aspect would be that while when we come to prismatic, where they use fuel assemblies, it's in some sense then similar to conventional light water reactors, right? Using assemblies. But when we talk about the pebble bed reactors, where they are using pebbles as a fuel, the problem or the uniqueness comes is that they are so small that there are no unique ID associated with them. In a light water reactor, when we look at the assemblies, there are unique identification associated with them at the top of the assembly, where they mark it, this is X number of the assembly, X, X1, X2, whatnot. But in the case of Pebble, there is no marking system that we can uniquely associate with a Pebble once we relocate, kind of, if that's the correct one. So the ID associated with is not there. So kind of it leads to this being in a pebble bed as a most likely it will be termed as a, if not already, as a bulk facility. HTGR, to talk about it. So presently, IE has employed safeguards instruments at the HTRPM reactor in China, which is a pebble bed reactor, using about 450,000 pebbles at a time. And while they have applied, considering China is a voluntary offer agreement and a voluntary offer agreement, and also these instruments are essentially for testing purposes, so not really that they are imposed for safeguard purposes. Now, considering as a bulk facility, and then the another aspect is similar to CANDO's, they are online refueled or PHWR pressurized heavy water reactors. They are being online refueled. The difficulty to count in the sense that the thousands of them makes it difficult to count, right? It's not like 200, 300 assemblies that we are using. And then another aspect is that they have graphite pebbles as well. So at the time of reactor startup, they have graphite pebbles initially in the core, sitting in the core, and then comes the fuel pebble, which kind of then circulates before, in some sense, a steady state achieved before that. After that, the graphite pebbles are kind of slowly removed until then. So there is another aspect, how to distinguish between them and account for that. And here is a kind of a snapshot of potential the safeguards could be applied. A concept level approach that will this kind of in some sense highlights. And this also provides opportunity to talk about two things, is the material balance area as well as the measurement points. So when we talk about this, FKMP1 is essentially pebbles are coming in the reactor side from outside. Essentially, that is flow coming in. So it's a flow measurement point, key measurement point, where you essentially weigh the container in which it is received for verifying whether whoever the shipper was, whatever their declaration was, does it match or not. So it's usually received in containers, then it's transferred, it's loaded in a potentially in a system, fuel handling system for loading in the core, and kind of forms a part of a closed loop system. It would be recirculated. Started with probably we'll check the integrity. If it's damaged along the way, then it will be removed as a damaged pebble. If it's not damaged, it circulates through checks for the burn up. Considering in the pebble bed reactor, they are expecting there will be close to 6 passes that the pebble will circulate through the core. And they'll check the burn up. If the burn up is not met enough, it's below the threshold that they identified to fully utilize it, they'll recirculate. And if it's met, then it will discard and it will be discharged to the spent fuel container. But in some sense, few of the measurement systems where the challenge will lie is to, in general as well, not this measurement system, is to verify this bulk material, verifying the enrichment before they are loaded in the core. In the core is integrity checks, as well as making sure that no other pebble are being inserted in that system. With the undeclared material has been introduced. The burn-up measurement, verifying that, considering IE at the moment uses, in some sense, burn-up codes that are well established and validated, but the challenge will lie to have such a similar established code for new advanced reactors. And then spent fuel, how to measure that before kind of being shipped offsite, something like that. Some of the challenges associated with them where the development efforts needs. Okay. Now, to talk about the liquid metal cooled reactor, in some sense, except for the coolant, I guess it's closely similar to light water reactor. Fuel assembly form, enrichment is slightly higher, LOU fuel. They may use blanket as well for breeding, which some of them are called breeder reactor. Let's say, for example, prototype fast breeder reactor in India. But the sodium and lead cooled reactor designs are popular of them. Sodium brings its own challenge as well. The fire safety issues that it warrants assessment needs are there. And then in terms of the experience with such a liquid metal cooled fast reactors, there has been prior experience with for the IEA to impose safeguards and do verification, but they have been in the past, not nearly for a decade or so, that they haven't performed any verification such facilities. Um, the 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 ability to use some sense the Cherenkov radiations or using visual inspections for fresh fuel, those sort of things are not the case anymore for applicable for liquid metal cooled reactor. Although there are other ways to do that for opaque um, coolant, but still it's a different aspect to work on. Another is based on the fuel cycle that this design such reactor designs employ. That could be transuranic waste as well. That could, in some sense, render the current measurement system ineffective, or or other ways unreliable with the confidence cannot be the same. Um, and to talk about verifying this, that what the assembly is put in the reactor and what has been taken out. This is a schematic of what the measurement system approach look like for such a design, where essentially they place a sodium and gamma detectors on a fuel handling system. So when they catch, or when kind of they hold the fuel assembly to put in the reactor, they're able to measure the signatures and verify whether it's a fresh or spent, and if it's fresh, is it as per the declaration or not, and so on. So that helps in some sense doing verification that would not be feasible otherwise. Um, it provides a level of um, verification that is beneficial and kind of meets the need. So such kind of unique ways, I guess, approach is required for meeting safeguards verification goals. Yeah. Now, last set of is the molten salt reactor. And presently, essentially, there are fluoride or fluoride-based designs that are being discussed, and um, where and this molten salt reactor covers both, where designs where that only molten salt is used as a coolant, but also as a fuel. And then there are variation of designs as well, where the fuel is molten salt, but it's not loose, and it's in kind of um, contained in an assembly in a fuel rod form. So there are designs of such variations as well. Mostly, again, it's either LEU or HELO fuel. But then there are variations of plutonium, thorium, uranium, plutonium, the fuel sort composition. And another aspect is, while the initial composition may um, be something, the makeup fuel sort may have different composition as well. So there is that aspect associated with it as well, that the fuel form as well as composition, physical as well as chemical form changes during the operation. So for the thermal based one, they're using graphite for moderation purposes, which kind of leads to oxidation issues and leads to limited life as compared to light water reactors. And so mostly where thermal designs, they're kind of having a life expectancy of, or design life of about 5 to 10 years at max, unless you impose a reprocessing system not reprocessing, my bad, processing system or polishing system, then you can have an extended life for these reactors. So uniqueness with MSR is that there are no prior safeguard experience, but there have been, and there is only one safeguard, only one operational experience with MSR is the molten salt reactor experiment and Oak Ridge National Lab, and which operated for over close to a decade, in 60s. But although while there is no safeguard experience, it's closely similar to either a reprocessing or pyroprocessing facility where the material is in the loose form, but the temperature levels are different, and in some sense the radiation levels are also different, right? Um, yeah, fuels are in the bulk form, so unique safeguards challenge compared to other reactors designs. High temperature levels, um, about 700 degrees Celsius, so maybe 1000 Kelvin, 1100 Kelvin-ish. Analytical facilities will be required on site to check for that pH levels in the system as well as for any monitoring purposes. So it brings another aspect on the reactor facility that is not common in current set of reactors. Um, and in terms of the approach, uh, this figure in some sense highlights a potential approach that is kind of proposed, at least for domestic safeguards, where essentially they do 3 MBA format, one for the fresh fuel area, second is for the reactor, and third for the spent fuel. The challenge lies in some sense is to verifying what is being fed in the reactor and then verifying the burn-up levels of the discharge fuel. And while ensuring if there are polishing system and processing system present, making sure that there are no misuse or diversion occurring from those connection points. So some of the challenges while I'm highlighting, it's also the efforts that are being pursued to address them. And I think with that, I'll end and happy to answer any questions.
Thank you so much, Dr. Shah. It looks like there are a bunch of questions for you in the Q&A. You can just kind of go through those and answer at your leisure.
First one is out of pay grade. So I'll skip. Is the item specific signed with the nuclear armed states, or does it include some or all nuclear weapons? So item specific agreements are with states which are not party to the nuclear weapons nuclear weapons treaty, NPT, and India, Israel, Pakistan, South Sudan, North Korea at the moment, in some sense, if I got that right, would be falling under this, under NPT, non-NPT. And the item specific, I think, applied right now is under India, Israel, and Pakistan. What is LOFs? Location outside facilities. So you can consider this as a kind of a building, let's say, outside the facility where there might be some nuclear activities happening, may not have nuclear material, or will not have nuclear material, then they are lofts, or they have nuclear material but under the threshold levels, things like that would be lofts. What makes the extended safeguard agreements harder to get a state to agree? What makes the extended safeguard agreement harder to get a state to agree to? Why have them extended when they're all good? Extended safeguard. I'm not sure what do you mean by extended safeguards agreement, unless I'm missing a point. I'll come back to that one afterwards. That's it. How frequent do inspector check a facility? Is there a certain limit to number of times a facility may be checked? So this comes down to basic, that what kind of material you have, in what form you have, uh, and how are you handling it. I think essentially this, and then this is straightforward, but then there are various aspects associated with as well, because IEA kind of follows a state level concept where they look at the state as a holistic, what sort of nuclear program it has. Based on that, it kind of determines. So, but if you have to give a generic example, let's say, for example, LWR facilities, light water reactor facilities, then it would be usually they'll be every year or so. The inspection would be, uh, and most likely they may do it during the refueling as well, from what I understand. Uh, but if you have a, I think, not reprocessing or processing facility, which will require some sense, like let's say, for example, um, Japan's facility where they're doing Roka show, then you'll have inspector present all the time, right? They have inspector station there. So that would be the kind of extreme end. How controlled can safeguard by design get? Is everything fully accountable all the time? So safeguard by design, it's the main thing is it's voluntary. Uh, so that's where the biggest challenge lies. And then second is not all are aware of it. Um, if you have seen other videos from IE or so, Jeremy Whitlock, and there are a few people who are doing a lot of webinars on this recently, trying and recently that it's more popular now, but they've been obviously engaged for a while. They are doing a lot of meetings and engagements with vendors, designers, under member state programs to get more buy-in from the designers. And in terms of fully accountable, so there will be, this is not like when you do safeguard by design, it's you're done. There will be still measures required. It's kind of a way to complement so as to minimize resources that may be otherwise required down the line. So as kind of it's a balance. As much as, let's say, for example, as much as research you do, there will be never some answers you can't find, right? So it's kind of a balance. How much research do you want to do between how much measures you want to impose now or later? So some things only will have to be done like through uh, routine inspections or DIQ verifications, things like that will be required that they can't bypass. What to do when a facility safeguards conflict with international safeguards? It's a good question, and I haven't got that enough exposure to say or come across a situation where the conflict lies. Usually, domestic safeguards are meant to support international safeguards. That should not be any concerns, except the conflict comes in is in terms of reporting errors or things like that when there are issues to be resolved. That's what they call it, transit matching. But apart from that, I don't know if there are any kind of outright conflict. Usually, then if there are any, they would have been resolved by the before the agreements are in place and measures are employed. So yeah, they are. Yeah, I wouldn't expect anything once they are done, imposed. Can you please provide some examples of a joint use equipment between IE state and operator? Ah, so I I'm not 100% sure, but there are cases in Rokasho where it's a joint use. Um, and I can find few more examples of it where there are being used. Maybe potentially they might be, I want to say in Canada, but I'm not 100% sure. But yeah, I can answer that afterwards, Nasreen. Uh, essentially, I think wherever there is nowadays where there are processing facilities, they'll consider that joint use. And I mean, in that sense, Rokasha would have it. Test reactors are not considered for safeguard by design. I would expect you were writing SDA for safeguard by design by IEA. I don't think that's correct. I think I don't think so. They'll consider any nuclear facilities of for safeguard by design. As I was saying, there are facility level to state level. So all of that get encompassed in their safeguard by design approach or concept. Thanks for your insightful lectures. I will like your response on safeguard implications that small modular proposes. So major challenge, I think, and I think with small modular reactor is going to be between two things is if they are sealed and there is not much nuclear material hindering in between, then how do they do safeguard measures? Kind of, let's say, for example, if they're not doing any refueling or any feed or makeup to the reactors for 3-4 years or 4-5 years, then are they going to sit back and trust on containment surveillance measures? Or would they come in and still do inspection? So that will be one thing apart from the technological challenges associated with it. I think that's the main one I would say in terms of safeguard implications, apart from what I've already highlighted. The role of IEA to ensure correctness in the wake of emerging threats that present in nuclear security. Yes, yeah, I mean, very obvious example is Ukraine, and it's difficult. And I think once you lose continuity of knowledge, then whatever only you can kind of re-verify, um, and it kind of poses a big loophole, right, in the system. But it's some things that are out of control, and you just have to work through negotiations to address. Few things there will be, as much as you try, can be sometimes out of your hands. So I know it's not the right answer, but I don't think there's a right answer. Uh, as far as I know, recently research said that microwave fuel will use sodium uranium as a problem that can't provide long-term operation because the multiplication factor becomes separated for few years operation. The problem is the composition of enzyme which may respond like that international does the problem solve yet? If it doesn't solve yet, how to solve the problems in this point of view? Uh, I mean, yeah, HEU based fuel are going to be tricky to safeguards because uh, when you have HEU, I think the frequency window goes down to 3 months, if I got that right, or 6 months between that, but under a year for sure. In that case, yeah, I mean, and if that micro reactor is, let's say, for example, on a ship, then how are you going to do that? So yeah, major problem or challenge lies in terms of for IEA to safeguard that. And yes, unique problem to work on, and I don't think there is an answer for that right now. Sorry. How does the polishing system work? So I'm not a chemist to answer that correctly, but I think it essentially has got hydrogen treatment, hydrogen fluoride treatment, things like that. And then it kind of has got some filters as well, let's say sodium fluoride, things like that, so as to trap noble gases as well as noble gases, fission products, as well as clear out impurities of oxygen or anything like that may build up. Redox reactions, essentially, there is also that would be part of it. And then that could be part of it. If we go stretch, would be processing, would be that you have thorium as well. Or things like that as a blanket that you kind of process and put it back in the core. That would be a step from polishing to processing. I think that's probably a small distinction between them, I think. Please, can you explain a bit more about molten salt reactor conditioning? Yeah, I think we are trying to see if there is a clear distinction, but every vendor seems to use it differently, conditioning, polishing. So if you ask a chemist, they'll be able to say it, but I don't know if exactly the vendors are using it appropriately, the similar definition wise. Conditioning, if I want to say, then it will limit only up to kind of temperature and things like that. Polishing comes as a little bit of more clearing out. Polishing, I mean, conditioning will be temperature, humidity, and pressure, things like that. And if I go to polishing, and next step would be that I'm also maintaining doing redox reaction. I think I would go to that end and filtering out other impurities, fission product impurities. That will be polishing. So I don't know if that helps, but a bit of still a distinction. I'm curious, how does the molten salt reactor work? We know that salt can make steel decay faster. Uh, so I haven't gone into the design, interior design, and I think nobody is really talking about it because of obvious reasons, uh, sensitivity associated with it and economic value associated with it. But the salt is in the salt. So when you talk, there is a fuel, you mix it with the salt, so that kind of becomes a fuel salt. And then you circulate, gets circulated within the system while there is a mod. So if it's a fast reactor, there is no moderation, then it would work fine. Kind of, it has got um, either some sense controller or things so as to maintain the reactivity as desired. But otherwise, if there are moderation involved with for thermal reactor, there will be graphite to moderate it, right? Uh, yeah, I don't know if I can say anything apart from that, what is already out there. There is no design information that I can provide that exactly address. And for obvious reason, they are still refining their design to address some of these issues, to be honest, right? That's why they are still under development. What occupation do the people creating safeguards have? Creating safeguards, or you mean designing, applying safeguards, or kind of developing safeguards, I will take it as. And uh, it varies. For example, I haven't joined, so, but people like my background who kind of work on safeguards approaches, people who are good with radiation detectors, who are facilitating safeguard application in the state, things like that. Things like that, people like that will be working on it. People like, including who are good with satellite images, open source analysis, things like people like that would be also working on safeguards in the safeguards field. Uh, yeah, there's a broad, yeah, it's interdisciplinary field, to be honest. What is the advantage of using salt, and what type of salt are you using? I'm not using anything, but to talk about the salt advantage, I think is the main thing is the process heat. I think that's the main advantage of using molten salt reactor, from what I understand. I'll go to next. Which are the biggest challenge in the design of safeguards for the waste storage system? Maintaining the continuity of knowledge. If it's going to be long term, how you'll ensure that it remains there, kind of thing. Probably that's the main one. And I guess Stuck is doing a good job of working on it, waste repository. So, and I think is involved with Safeguard by Design for them as well. So there might be joint use equipment there as well for if nursery, I missed the name, sorry. So that might be another example where joint use equipment might be there. Could you please elaborate on the methods or instruments used by the agency to verify nuclear material? Let's take spent fuel in nuclear power plant again. So I think this one is, if we talk about the light water reactor, Cherenkov radiation viewing device is there. I think there are few of them of similar type that they use. There are also ones where, so Cherenkov, you kind of hold it. It's kind of a thing that binocular, let's say, for example, that you hold it and kind of view it. But then there are also detector systems that you put it in the spent pool as well to do the measurement, which uses gamma spectroscopy and neutron measurements to do the spent fuel verification. And I think 2011, there is a safeguards equipment, something like that, IEA document. That would be great reference to look at what sort of instruments they use for spent fuel verification. From all the reactors you mentioned, which reactor is more efficient for converting energy? I think molten salt is the best, considering it's a high temperature. Yeah. Well, how is the inspection done on already existing reactors? I think there is a good video from the IEA on YouTube, a day in the life of inspector, something like that. That will provide you a good idea of how it is done. But usually it's like depending on the facility size, it's kind of a 1 day or a week or how long may be required is to do the nuclear material accounting, do the measurements, do the continuity of knowledge checks, things like that. Take do the measurement, use the sampling, random sampling to do some measurements of the new material or something like that. So there are various aspects associated with to accomplish that. So yeah, it's a little more involved. It can be intensive. They do need to do a lot of things. And I think they walk like 5 to 10 kilometers over that 1 day, something like that. How can inspectors know the released material of the fuel meet after how can inspector know the released material of fuel meet after commissioning? What instrument? Oh, so I think this goes to burn up measurement. I think that's what you're going. How do they know that whatever is left is correct? So by the time meet after commissioning, wait, not decommissioning. Okay. I don't know how to say this released material of the fuel. If you want to rephrase it at the end, I can answer that again. Okay. So can you please explain the trade-off between implementing additional safety features and the potential increase in costs associated with nuclear power generation, taking into consideration long-term implication in this decision, public health and so, I mean, for example, I would say molten salt reactor and pebble bed reactors are kind of really inherently safe. Compared to light water reactors because of being molten stage there, and then pebble bed being using a pebble that have high melting temperature offers a little bit more inherent features of retaining fission product releases when they undergo severe accident. So offers a bigger margin, safety margin. So I think because of those design itself and trying to meet that safety requirement that they are kind of running into extra cost, right? So, because those designs are new, that they need to undergo rigorous kind of scrutiny before they can be licensed, right? So that's that they are running into. But if ones get deployed, like HTTRPM is deployed, right? So now next iteration of them after they suffer like 2 decades of delay, moving forward, I think they'll be much faster about it. Same with
Okay.
molten silver. Yeah.
Thank you, Dr. Shaw. Looks like we're out of time. Thank you so much for your talk, and thank you everyone for coming. We'll see you all next week. Thank you so much.
Yeah. If you have questions, feel free to send me email.
Thank you, Dr. Shaw. See you.
Thank you.